Hello class, today we are starting the first of two videos on optimization problems with exponential functions. So in this note you will see there are 6 examples and today I will be doing 3 of them. So we remember optimization questions from chapter 3 and these will all have to do with exponential functions. So remember, optimize means to determine values of variables so that a function representing quantities such as cost, area, number of objects, or distance can be minimized or maximized. So in other words, we are looking for when the derivative is equal to 0. Again, that is because when the derivative is equal to 0, that means the slope of the tangent is 0. That means the tangent is a horizontal line and therefore at a potential maximum or minimum. So example 1, people who are immobile for long periods of time due to injury are sometimes given blood thinners to prevent strokes and embolisms. The liver gradually breaks down any drug injected into the body. Suppose the concentration of the injected drug is given by the function C at t equals 10t e to the negative 0.01 t, where C at t is the concentration of the drug in the bloodstream in milligrams per liter, and t is the time after the injection in minutes. So determine dc dt and interpret the meaning of its value. So dc dt simply means to find the derivative of this function. So it means the change of concentration with respect to time. So let's find that. So we can say dc dt is equal to the same thing as c prime at t. Okay, so look at this as a product rule function. So we have 10t as our first function, so we'll leave it the same. And then take the derivative of e to the negative 0.01 t. So we know that that is just e stays the same. And then we multiply that by the derivative of the exponent, which is just negative 0.01. And then we add, now we take the derivative of 10t, which is just 10, and then multiply it by just that second function. So notice that we have this e to the negative 0.01 t twice. That will happen all the time with exponential functions because of the nature of the derivative. So notice here that we can factor out e to the negative 0.01 t. And that will be very important for solving. So then notice here we get 10 times negative 0.01, which gives us just minus 0.1 t, and then plus 10. Okay, so this represents the rate at which the concentration of the drug changes over time. Okay, so if the rate of change is positive, that means the concentration of the drug is increasing. And if the rate of change is negative, then that means that the concentration is decreasing at that time. So we can expect with drugs that there'll be a certain period of time where the concentration will increase until it hits its maximum, and then it will decrease until it leaves your body. So what is the maximum concentration of the drug, and when does this concentration occur? So this is the same as setting our derivative equal to 0. So we take our e to the negative 0.01 t, bracket negative 0.1 t plus 10, and set it equal to 0. Now, think about this as either this equals 0, or this equals 0. Now, this has no solution, okay? Because this on the left is actually an exponential function, okay? So it actually has an asymptote at 0, a horizontal asymptote. So this actually has no solution. So this is the solution that we want to get to. So we get 0.1 t equals 10. So t equals 100. So that is the solution, okay? So it says, when does the concentration occur? Well, we now know it occurs at 100 minutes or 1 hour and 40 minutes. To find what the concentration actually is, we can put this back into the original function, not the derivative. And we get 10 times 100 times e to the negative 0.01 times 100. And if you put that into your calculator, you get approximately 367.88, and that's in milligrams per liter. Okay, so we can conclude then in a nice little sentence that after 1 hour, 40 minutes, max concentration of, let's say concentration of 367.88 milligrams per liter occurs. All right, period. Okay, the drug must be readministered if the concentration falls below 100 milligrams per liter. Determine the number of hours until the drug should be readministered. Okay, so we need to find now when this function is equal to 100. So we want to know when the original function equals 100. Okay, so it's really important that you are able to interpret when you need to set the derivative equal to a number or when you need to set the function equal to a number. In this case, it wants to know the concentration, so that refers to the original function. So notice we can divide both sides by 10 to get 10 here. Okay, so we can't solve this algebraically, unfortunately, since there is a t here in the place of the exponent, okay? Oh, sorry, in a place other than the exponent, okay? If we only had an unknown in the exponent, then we could actually do this. So we would need to solve graphically. Okay, so we can go over to GeoGebra. And I have one there for the next one. We can go to GeoGebra and solve for this. Sorry, I thought I had the other one set up. Okay. All right, so here we have f at x equals 10x, okay, and then you have to do times or else it won't work, e to the power negative 0.01x, okay? You have to put this times in here or else it won't work. Okay, and we know we're going to concentrations greater than 100, so we need to go over here to our settings and change our Y max to, like, we know the max is 367. Sorry, yeah, 367. So let's go up to like 375 as our maximum here. And we know that it happens after 100 minutes. So we need to know, we need to go to at least, I don't know, what should we try, like 200 minutes and see what that does. Okay, so let's just see how this looks. Okay, so we're looking for when it crosses 100. So you can see we haven't gotten there yet. So you have to play around with GeoGebra in order to find where this is happening. So let's try 500 for the maximum time. See what happens there. So there, now we can see that at 100, that's at about 360 or so minutes that's happening. Okay, so 6 times 6, so yeah, 6 hours. So you can say graphically, you determined that it was approximately 6 hours using GeoGebra. Okay, so let's go back to the note. So that was example 1. Okay, so we need to be able to identify when we can solve graphically and when we cannot. Okay, so now we have 2 different drugs that are used to treat an illness, drug A and drug B. So we want to calculate the maximum concentrations for each to 2 decimal places and the time when those concentrations occur. So this is just a process of setting each derivative equal to 0, okay, and then making some decisions about that. So CA prime at t is, so we keep our first function the same, 1.47t, we can see that as a function, and then times the derivative of that e to the negative t, which is e to the negative t times -1. And then we add 1.47 e to the negative t. So notice here we can factor out a 1.47 e to the negative t. Sorry about that. That's a negative t. And then we're left with negative t plus 1. Okay, so when we set this equal to 0, notice that again, this first part has no solution because this is an exponential function which has its horizontal asymptote. So really it's just minus t plus 1 equals 0 or t equals 1. So the first drug has its max concentration at 1, okay? And then if you put that into the function, you get 0.54. Okay, now our second function, CB at t, so we're going to leave t squared how it is, times e to the negative t times -1, plus 2t e to the negative t. So again, we can factor out t and an e to the negative t, and we're left with negative t plus 2. So same reasoning when we set this equal to, let's say prime. When we set CB at prime at t equal to 0, this will have no solution, so you just get t equals 2. And when you put that into the function, you get also 0.54. So they both have a maximum concentration of 0.54, but the first drug, it happens at 1, and the second drug, it happens at 2, and that would be in hours. Okay, so if the drug must be fast acting, which drug should the patient receive? So this would be drug A, since it reaches its max faster. Okay, and if the drug must be active for a long time, which should be administered, this would be drug B, because it takes longer for it to reach 0. And if you're not sure why that is, you can go to GeoGebra, and that's what I had graphed here, and graph each of them. So drug A is the green one, so you can see it hits its max at 1 hour and then tapers off, after about 5 hours. But the blue is drug B, and it takes longer to reach its max, but then tapers off more slowly and is in your system for more like 7 hours. So if you can't reason through that algebraically, you can check that the graphs are that way. Okay, final example for today, or for this video at least. Okay, a mathematical consultant determines the proportion of people who responded to the advertisement of a new product after it has been marketed for t days is given by f at t equals 0.71 minus e to the negative 0.t. So notice this is a proportion of people. That's very important. That means that the answer is a percent of people, not a number of people. Okay, so the area covered by the advertisement contains 10 million potential customers. So obviously, like 100% proportion would be all 10 million people. A 50% proportion would be 5 million people, okay? And each response to the ad results in a revenue of 70 cents on average, excluding the cost of advertising. But the advertising costs $30,000 to produce and a further $5,000 per day to run. So they first want us to determine this limit as t approaches infinity of this proportion function. So basically, what is going to happen if time goes on forever? So if time continues forever, what is the proportion of people that will be responding. Okay, so let's figure that out first. So the limit as t approaches infinity of f at t is equal to the limit as t approaches infinity of 0.7, 1 minus e to the negative 0.2 t. So what's happening here? Well, as t approaches infinity, okay, think about the graph of e to the negative 0.2 t. Okay, that will approach 0. Okay, because it is a graph that's shaped like this. Okay, so therefore this limit, so this will go to 0, will approach 0.7. Okay, so that means if the ad lasts forever, then we can assume based on this that 70% will respond, or 7 million people. Okay, what percent of potential customers have responded after 7 days of advertising? Okay, so that is just, we don't actually need to do a derivative there. That's just our function after 7 days. Okay, so that gives us approximately a 0.53 or 53% of people if you put 7 into that function. Okay, so write the function P at T that represents the average profit after T days of advertising. What is the average profit after 7 days? Okay, so now we have to come up with a profit function. So we have to look at our revenue and our costs. Okay, so our revenue at time, our profit at time is equal to our revenue at time minus our cost at time, T being number of days. Okay, so our revenue is how much money we are taking in. Okay, so that's how much money we're making. And our cost is how much we're spending. So our revenue then is based on 0.7, which comes from 70 cents per customer, times our total number of potential customers, which is 10 to the 7, times the proportion of them that will respond, which is based on f at t. So this is the f at t function. Now, I don't love, to be honest, that this question has two 0.7s. It's confusing. This 0.7 refers to the 70 cents of revenue the company gets, and this 0.7 is from the f at t function. So this function here is f at t. So we have 70 cents times the total number of potential customers times the proportion that will respond. So if we can collect like terms here, we have 0.49 times 10 to the 7 times 1 minus e to the negative 0.2 t. Okay, so we can take a decimal place out of here and make this 4.9 times 10 to the 6 times 1 minus e to the negative 0.2 t. Okay, so that is our revenue function. And so we can also come up with our cost function. So our cost function is 30,000 plus 5,000 per day. So plus 5,000 T. Okay, so there's our revenue function and our cost function. So let's put it together into a profit function. So P at T equals 4.9 bracket 10 to the 6 1 minus e to the negative 0.2 t, and then subtract 30,000 and also subtract 5,000 t. Okay, make sure those are both being subtracted. Okay, so if we find our potential profit after 7 days, we just put 7 in for t in both of those spots, and you would get $3,627,000. Okay, now of course we want to know, part D, how many full days should the advertising company run the campaign in order to maximize the average profit? So let's assume they have an advertising budget of $200,000. So this is the equivalent of asking, well, we have to figure out how many days they could even run it for. So we need to figure out our restrictions first. So our costs, which are 30,000 plus 5,000 T, have to be less than or equal to 200,000, which boils down to the fact that T has to be between 0 and 34, because this would give us 34 days. So now we have to find the derivative of our profit function within this restriction. So P prime at T is equal to 4.9, 10 to the 6, okay? And then we take down this 1 goes away. We take down this negative 0.2 and a negative. So, okay, I'll just show it. So it's negative E, negative 0.2 T, but then times negative 0.2. And then we subtract 5,000 from this part of the derivative. Okay, so that is the beginning of our derivative. I'm just going to change it a bit now. So this negative and this negative give a positive 0.2, which I'm going to throw out front, times 4.9 times 10 to the 6 times E to the negative 0.2 T. And then that's all subtract 5,000. Okay, so this is 0.98, but I can make it 9.8 if I change this to 10 to the 5. Again, just wanting to leave it, move my 10 column over there. And then E to the negative 0.2 T minus 5,000. Okay, so now I want to set this derivative equal to 0 and solve. Okay, so what I'm able to do here is get 9.8, 10 to the 5, E to the negative 0.2 T equals 500, okay? Or sorry, 5,000. So I'm setting this derivative equal to 0 and then moving the 5,000 over. So now to be able to solve for this T, I need just the exponent. So E to the negative 0.2 T equals 5,000 divided by 9.8 times 10 to the 5. So this is all just a number that your calculator can handle. So now what we need to do is take the natural log of both sides, or the ln of both sides. So when we take the ln of both sides, then you will get negative 0.2 T on the left equals the ln of all that junk on the right. And when you do that, you get T equals about 26. Okay, if you need help with that from me, let me know. Again, from here to here, we're just taking the natural log of both sides, which brings that exponent down, and the ln of E is just 1. So I can show you that in more detail. Okay, so now you can test P at 0, P at 34, and P at 26, and you'll find that this is the winner with $4,713,000. Okay, so that's the beginning of optimization with exponential functions. Thanks for watching. Hope you learned lots.